Alright, this is our last video for the class, astronomy video number 3. And your last question of the day is, if you could have any superpower, what would it be and why? So go ahead and answer that in those blanks there, and we'll get started with our lesson for today. So 24.3, so chapter 24, section 3 from the Earth book, we're going to talk specifically about the sun today. The first thing you need to know about the sun is the structure that it has. So we have the corona, okay, that's the outer layer here that you can see with this shining light. We have the photosphere, which is a very small layer. You can also see it blown up here. This is your photosphere. It's this very thin outer shell layer. Okay. We have a convection zone. That's where things are being heated up. A radiation zone that comes out from the core. You can see your core. We also have the chromosphere. Okay. Those are kind of the sun rays that are specific and coming straight off of the sun. It's not just the light that we see, but it's actual rays of heat. We have prominence over here. We have some granulation, so some of those sun features, and then we have sunspots, of course. So a sunspot, that's a dark spot that's on the sun. They appear dark because of their temperature. It's about 1,500 Kelvin less than that of the rest of the solar surface. So it's a lot cooler spot, okay? So as you can see here, here's our sun, here's a little bit of a sunspot, and if you zoom in close, you can definitely see it's this darkened area, so it is cooler in temperature. Prominences. These are huge cloud-like structures. They consist of chromospheric gases, okay? So that's all of this extra gas that you see here, kind of like our clouds, but this is in a very heated gas form. We also have solar flares. Solar flares are very brief. They're usually about an hour in length. And they are outbursts that appear as a bright spot right above a sunspot cluster. Okay, so it's kind of like this releasing of energy or releasing of heat that's right above a sunspot where it's colder. We also have auroras, and those are changing light from solar radiation. Nuclear fusion is important. It's a reaction that gives the sun its energy. So it takes 4 hydrogen and it transforms them into a helium atom. Okay? And it releases a tremendous amount of energy when it does this. So if you look at like a periodic table, for example, the one I have on my wall, you can see that hydrogen is on one side, helium is on the other. Okay, so to get from one side to the other, it's a tremendous amount of energy. So nuclear fusion, just so you're clear, we have hydrogens come together. They will collide, and when they do, you get some helium. Okay, so hydrogens coming together, you get helium. Chapter 25, section 1, so characteristics of stars. We've talked about stars a little bit already. Star color and temperature. A color is a clue to how hot or how cold a star is. Very hot stars with surface temperatures that are above 30,000 Kelvin are emitting energy in the form of short waves. Okay, so they are going to appear blue because blue has a very short wavelength if we look at the electromagnetic spectrum for light. And we talked about that already. Red stars are a lot cooler because they are emitting energy in longer wavelengths. Okay, so they appear red. And stars that are in between, stars that are between 5,000 and 6,000 Kelvin, those appear yellow, much like our sun. Now, keep in mind that you are not going to see red, blue, and yellow stars in the night sky. They are so far away that you cannot clearly depict the color. But there are ways that we can look at that. Okay, now a light year, that's the distance light travels in 1 year, and it's about 9.5 trillion kilometers. Okay, or in other words, this big long number down here, 5.87 times 10 to the 12th miles in 1 year. So that's pretty far. Stellar brightness, it's something that we call apparent magnitude. It's how bright a star appears from the Earth. So you can see here, we can see red, blue, we can see yellows, but we don't see this much in our night sky. Now, if we have a telescope and we're looking at them more closely, you can clearly see the colors. So there are 3 things that matter when we're talking about apparent magnitude, when we're talking about brightness: how big it is, how hot it is, and how far away it is. Those are the 3 most important things. So if it's very big, it's very hot, and it's very close, you're going to be able to see that apparent magnitude much better than if it's small, cold, and very far away. We also have something called absolute magnitude. This is how bright the star actually is. And yes, the sun is considered to be a star. So it tells you the apparent magnitude, what we believe it to be, it appears to be, and then the absolute magnitude. Okay? So the more negative, if you look at these numbers, the more negative a number is, the brighter it is. The more positive, the dimmer it is. Okay? So the sun is actually a 5.0. So it's actually pretty dim in comparison to the star named Deneb, which is a negative 6.9. Okay, so appearances can be very deceiving. Our eyes can play tricks on us. What you see here is a Hertzsprung-Russell diagram. It shows a relationship between absolute magnitude and temperature of stars. So it will take those numbers that we just saw in that chart and it will relate them in different ways, either in pictures, charts, tables, graphs, that sort of thing, to compare the temperature and the absolute magnitude. So, for example, here is one of those diagrams. So we have blue, which is really cold, and we have our red. We have white dwarfs here. We have what we call giants, and then we have supergiants. Okay, all of these are different types of stars. Chapter 25, Section 2, Star Birth. So how are stars made? So we start with what's called a protostar stage. It moves into a main sequence stage, and then we have what we call a red giant stage. Okay, so at birth, it starts as a nebula in all 3 cases. Okay, it goes into the protostar in all 3, goes into main sequence in all 3. It then, if you look, medium mass and massive stars hit the red giant phase, and then that's where they split. It can either become a planetary nebula and become a white dwarf, then a black dwarf, or it can become a supernova explosion and give you a neutron star or a black hole. Okay, so massive stars can be very dangerous, but low mass stars, after we hit that main sequence, it just automatically transfers into a white or a black dwarf. So burnout and death. Yes, stars burn out. Yes, there are star deaths. All stars, regardless of their size, will eventually run out of fuel, and they will collapse because of gravity. And when they collapse, that is when you get that black hole. So death of low mass stars, they transfer from a white dwarf to a black dwarf. If it's a medium mass, again, it still goes from a white dwarf to a black dwarf. And if it's a massive star, if it's a supernova, that is where you get your black hole. So only the massive ones can become a black hole when they collapse. All right, chapter 25, section 3, and we're almost done for today. We're going to talk about galaxies. Galaxies are considered to be groups of stars, dust, and gases that are held together by gravity. As you can see here, we are in a galaxy. The name of our galaxy is what? The Milky Way, right? So the Milky Way, it's said to be that there's more than 100 billion stars in our galaxy alone. It's a very large galaxy, and it's spiral galaxy. Okay, so it's said to be about 100,000 light years wide. Now, if you'll think back a couple of slides, we talked about how far a light year is. Okay, so if you can equate miles and multiply that by 100,000, that would tell you how wide our galaxy is. It's pretty big. So spiral galaxies kind of look like this. It has that spiral kind of S shape to it. We have elliptical galaxies, like this one. It looks kind of oval shaped. And then we have irregular galaxies. So they really have no shape to them at all. We also have galaxy clusters. So again, no real shape, but everything is clustered together as one. Now, our universe is expanding, and we have what's called Hubble's law. Okay? It says that galaxies are retreating from us at a speed proportional to their distance. Okay? So if they're really close to us, they're going slower. The farther away they get, the faster they go, because they are no longer held by our gravitational pull. Red shifts of distant galaxies are indicating that our universe is expanding, just like we talked about on our last video. So for example, if you have some raisin bread, and this is dough before you put it to rise, all of these pieces are really close together. And then a few hours later, those pieces are really far apart. Okay. Big Bang Theory. We haven't really talked about this a whole lot. It states that at one time the entire universe was confined to a dense, hot, supermassive ball. And then in a violent explosion, all of this material hurled into many different directions. Now, this is a theory, okay? This is not truth. There are facts to support it, but there are facts to support other theories as well, okay? So don't put all your eggs into one basket, as they say. So according to the Big Bang Theory, the universe is expanding, evolving, and cooling, which we do know that we are expanding. Things are cooling down. We are evolving. But again, this is a theory, so do not count this as complete truth. Okay? And this is the last slide, so we are done with videos and you are done with notes for the semester. Well done.